Hello, good morning, everybody. It is my pleasure to welcome all the participants today for this workshop. I welcome all the eminent speakers and guests to grace this workshop, and I heartily welcome our chief guest, Mr. Shanmugam sir, from SRM Institute of Science and Technology, for joining in this international workshop on machine learning. Now, our HOD sir, Mr. Krishna Kumar sir, is going to speak a few words.
Good morning to one and all here in online as well as the offline dignities. Myself, I am Dr. K. Krishna Kumar, Associate Professor, Department of Computer Science, Artificial Intelligence and Machine Learning. It's my honor to organize international hands-on workshop of artificial intelligence and machine learning with the Google 2023. In this special day, I would like to thank our honorable chairman and dynamic vice chairman, Mr. R.V. Srinivas Karu, and our respected principal, Dr. M. Mohan Babu Karu, and all my dear faculties, HODs, and faculty coordinators of Sri Venkateswara College of Engineering. The last but not least, the most lovable SVSET students, especially the backbone of CAC, Artificial Intelligence and Machine Learning students. Now, I'm pleased to share our SVSET from the RVS group is excellence in academic for successfully run in 38 years with accredited by NAC A plus grade, accredited by Tier 1 NBA, and also affiliated by the JNTU Anandapur. Also, I'm very proud to stay. Also, I'm very proud to say that our SVSET ranked in 198 among the top engineering college of by NIRF 2022. Now I request our honorable. Now I request our convener, Mr. V. Saravana Kumar, Assistant Professor, CSM Department, to share the introduction about our chief guest and eminent speaker, Dr. S. Sanmugam, from the SRM University, Katangulathur. Please, sir.
Yes, sir. So first of all, I'm thankful for the management and for our department as well as our students for supporting the permission and also their cooperation for this event to be. So this event is about international workshops on. I am very pleased to inform and also share about the today's experts, Dr. S. Sanmugam. Dr. S. Sanmugam is currently working as a assistant professor in the Department of Computing Technologies at SRM Institute of Science and Technology, Katangulathur campus, Chennai. He has more than 8 years of teaching experience, more than 5 years of research experience, and along with that one, 2 years practical experience in the industries. His main areas start from miscellaneous and now is totally involved in the quantum computing, the real technologies. So he published machine learning, data science. Now he is working practical with quantum computing with outside place. Until now, Star has been served for this society the way of publishing the book chapters, patterns. So he has been the author for 12 well-indexed journal with SCA and Scopus through 3 book chapters and 2 international patents. He is also 2021, and also he published another book that related to smart vehicle systems in Lambert Academic Publishing. Dr. Sangam is not only known for his expert knowledge, also for his supervisors in SRM University. He is a recognized research supervisor in SRM University. Now, welcome Dr. Sanmugam to share knowledge for our peoples. Dr. Sanmugam, please.
Thank you, Saravanan sir. Am I audible? Sir, am I audible? Hello. Saravanan sir, am I audible?
Thank you.
Hello. Hello. Anyone let me know? Am I audible?
Yes, sir.
Yes, fine. Thank you. Thank you for giving me the opportunity. I am Dr. Shanmugam from SRM University. So I directly go for the talk. I don't know my screen is visible, right?
Sir, you are audible and your screens are visible, sir. You can start your words. Thank you, sir.
Thank you. Thank you for giving me the opportunity. So today we are going to get some insights about the quantum machine learning. So nowadays it is a very trendy field. So everyone will speak about that quantum, right? Sir, is it an interactive session or only a lecture? Saravanan sir? Hello. Okay, fine.
Yes, sir.
So we are going to discuss about what is quantum, and then we have some hands-on experiments that how to handle with the quantum machine learning. Right? So the first thing is, so the computer technology will evolve many years, that we know, but the trend is towards a quantum. So quantum in the sense we are reducing the size and exponentially we are increasing the speed of our normal computer. So that's the thing. So nowadays we have a classical computer that we will able to do machine learning, deep learning, right? Everything we will able to do on the classical itself. But the trend is now to reduce the size and exponentially have to increase the computing capacity. Now the researchers are moving towards a quantum. So quantum that we are not seeing so far the hardware, but we have some set of. Am I audible? Can anyone reply me?
Yes, sir. Audible.
Okay, fine. Thank you. So, in order to solve a complex problem, what the classical approaches will fail. So that is the thing. We move to the quantum, right? So now we are in the entry level. So most probably the researchers are doing some research and they are trying to find the efficient hardware. But before that, we have some simulated results we have, right? So that is the thing. So quantum is nothing but according to physics. So as a computer people, we can't able to concentrate more on and the last one is a inference that we know. Inference is nothing but the connection between the two or more networks, right? So that is available on the quantum systems, right? So quantum computing is used for the system calculation. That is a that we already know. In a classical system, we have a bits, zeros and ones. But in a quantum computer, it is generally called as a qubits, right? So qubits is nothing but, as I already said, the values between lies between 0 and 1, right? So that is a thing of quantum computing. So the three things we have to know. One is the superposition, entanglement, and inference. These are all the basic building blocks of quantum computing. So superposition means in order to identify the which state. So if let us consider if there is two inputs, one input is in a zero state, and we will easily able to find the other input is in another state. So in a quantum, if we find the one state, then we will easily able to find the another state. So that is a superposition. Entanglement means connection between the layers, and the last is a interference, right? So these three are very important. And generally speaking, in a classical computer, it is called as a bits, but in a quantum computer, it is generally called as a qubits, right? So what would a quantum computer will do? See, so this is the thing. If the quantum computer would able to handle more issues. So in a classical also we will able to do, but at a certain time it won't work if all the memories are utilized, right? So that is the reason we go for a quantum. So quantum means automatically the order will be shrink, and we will able to get the speed of the component will be exponentially increased. So the best option is particular amplitude. The computer system must be in a superposition state for this function. We can't be able to find whether it is in this state or that state, right? So that depends on the hardware. And these are all the three crucial things that you have to know about quantum. That is a dedicated space and strategy for sending the signals to the qubit, and how the traditional computer commands to the system. So these are all the general things. So is a quantum computer real? Definitely it is a real. The peoples are working with, and they are facing a lot of problems for designing, but anyhow within 2025 IBM will release a basic part of quantum. Now they are using a simulator which is named as a Qiskit. So Qiskit, Pennylane, there are a lot of compilers are there in order to simulate a quantum. But IBM Qiskit is a very wonderful thing. We are going to discuss about the Qiskit also, right? So this is a thing. Experts predict that it will become a standard in the future. So at a particular stage, there is no classical computer. So wherever we go, we will able to see only the quantum computer. Definitely it will come. So this is a nature of advancement, as we already know. In the early days, we have a simple mobile. Now we have a touch, and in order in the future, definitely it will be shrink into a small handheld device, right? So this is the thing. And in the modern world, so this is a main example. As a result, researchers may set up a digital equivalent of a lab. So now we are in a simulation, like virtually we are working, but future we will get the hardware. So these are all the types of quantum. One is analog quantum, and next is a quantum annealer, and the third one is a universal quantum. So these are all the three basic advanced techniques in quantum computing. So first, quantum analog quantum in the sense, so it's a middle tier. So it's capable of solving the real issues at once. So it is generally operates with 50 to 100 qubits, right? So it's a very fast compared to the normal GPU system, right? Then the second is a quantum annealer. So this is nothing but limited and gets performed similarly to the traditional computers, but it's focusing on a single activity at a time. So that is a second thing. And the third is a universal quantum. So it will able to handle around 1 lakh qubits at a time. So this is a very advanced thing we have now is a universal quantum. Right? So these are all some applications. So first is a simulation. We will able to simulate whatever we have in our mind related to the quantum. Now we have an excellent environment to set up that simulation. And the second thing for using a quantum computing is optimization. So this is a very major phenomenon in quantum. So we are optimize a large number of futures into some meaningful futures. We are going to pick out from the large futures into a very important future. So like a logistics or traveling, so air flight, everything nowadays they are trying to shift from normal classical to that quantum optimization. And the third one is the cryptography. So like a finance, so and your share market, so everything under banking sector, so everything they comes under the quantum cryptography. So if your research field is a quantum cryptography, then you will easily able to adapt in a quantum. So that is not a big deal. So once we can learn some set of basics, definitely we will able to crack. There are a lot of opportunities in quantum cryptographies also. And the next part is machine learning. So that is a thing. So it is hard to implement since it requires a lot of time and money. But the researchers are working day by day to increase the speed, right? And data search. So like supervised learning, semi-supervised learning, everything we will able to handle with the machine learning. And the last is a data search. From the last decade itself, we have a significant data. So this work will able to search that. I mean, this quantum based systems is you retrieve the data very fast compared to the traditional. So these are all the applications. So among this application, we are mainly focuses on machine learning. So in the practical session, we will discuss how to develop a classical machine learning model and how to compare it with the quantum machine learning model. That is a plan today. Right? So, and these are all the advantages which take a large amount of data and it will speed up the processing time and it is more efficient in the long run. Right? So the race in a quantum computer is, so a few frequent issues that arise during a manufacturing. So that is a major problem while they plan for a hardware, right? And the development of physical architecture with adapting the qubits and improving the speed and making the functional replacement components. So what are all the components we are going to replace? So that is the major concern nowadays. The researchers are facing for developing a real quantum, right? And they are expanding the physics along with the physics and along with the mechanical people. They are every day they will work and definitely we will achieve a good quantum based hardware setup as soon as possible. Right? So now we focus on quantum machine learning. So machine learning is established by a successful interdisciplinary field, right? So it is in a quantum computing, gives rise interesting areas, right? So can anyone tell what are the types of learning available?
Sir, the most
Hello.
hello, sir.
Yes.
There are different types of learning methods we are having. We can classify it as supervised, semi-supervised, unsupervised, reinforcement learning.
Yes, sir. Right. So what we did in a supervised learning, from participant side, anyone?
Category, sir. Subcategory of machine learning.
Okay, that's okay. But what is supervised? Other anyone studied?
Sir, labeled data sets to train algorithms, sir. To classify data.
So we have a labeled data exactly. So for a supervised learning, we have a class labels. Right? So that is the thing about supervised learning and unsupervised learning. So unsupervised learning is nothing but we have not a labeled data, we have only the data. So we go for some clustering based concepts on unsupervised learning, right? Then reinforcement based on the action and based on the response, we will react, right? So this thing. So in a quantum machine learning is also the same scenario, but generally speaking, there are four important components are there, right? So one is a quantum data with quantum computer. Then quantum data with classical computer. And the third one is classical computer with classical data. And the fourth one is classical data on a quantum computer. So I hope you understand there are four different types of categories in quantum based learning. Among that, so most probably the researchers are working on classical data in a quantum computer. So the main research focus by the researchers is the classical data is applied in a quantum computer and they will analyze the performance between a classical and quantum. I hope you understand. So we directly go for the practical session. Just a minute, I will share my screen. Is it visible?
Yes, sir.
Okay, fine. So the main plan of this hands-on is to first we run the classical computer with classical data in a classical computer. So that is the first part, and we will analyze the performance. So once we analyze, then we apply the same data and we are able to check in a classic quantum computer, and we will compare the performance, right? So this is the thing. So for that, listen, you have to we will work in a Google Colab itself. That is everything that QuizKid will provide. So before working on this, I hope you already worked on Google Colab, right? Is there anything needed for how to work in a Google Colab? You have already enough idea, right? Or is anything needed? I will update you. Hello.
Sir, please can you brief that how to use this particular platform?
Okay, fine. So for this Google Colab, if you are new to that, just you go log in your Gmail. In the Gmail, you just go for a drive. Inside the drive, is it visible, right?
Yes, sir.
New.
Yes,
Inside
sir.
the see in the drive, you go for a new and you go for a more. I am already work with the Google Colab so that it's visible. If it is not available in your drive, you just go for connect more apps. In this, you just type CO collaborate. You have this one. You just click it, and it will automatically install in your Google Marketplace. Then, if it automatically install, you just check it in that here. You check it, and there is an option available in your drive is Google Colab. Right? Once you click it, it will come there. So it's already all the basic libraries of NumPy and Pandas are predefined. You no need to install anything like a Jupyter notebook. So you will be able to work on this notebook itself. You will just change the name. For example, I just put hello world. So it changed. Complete project name is changed. Now, after getting this screen, you just click the connect button and just wait for some time. Once you get a tick for the tram, it's installed, right? Then after this, it having a two sections. One is a code part and another one is a text part. In the code part, you will type the code and on it, you just click this cell, it will automatically run. Like for example, so so this part is having a two sections. One is for typing a code and another one is typing a text field. So whatever you want, you just like Python, it's also used as a calculator also. So once you have a 2 plus 3 and you just click the run button, it will give a result, right? So it's like our normal Python notebook. And if you want to add some text before that line, you just use this like world. And if I want to make this as a bold, you just click that. What happened? It will give a toggle. Then so you will be able to type a text as well as Python code. Both we will be able to do, right? Then after that, so after this, with your Google Drive, so there is one option called C. In this folder, you just click here and you click this mount drive. Once you click it, it asks you to connect the drive. So once you give, see, your drive will be automatically connected here. So based on this, you will get all the data from the drive. So this is one of the ways are there. But you can directly upload your data also by using this field. You directly upload here also, right? So this is a way to connect your Google Colab with the drive, right? Is there any doubt? Is there any doubt? That connection
No, sir.
Colab?
No, sir.
Then now we are going to print the hello world. Listen, just print inside that. Just give hello world. Like normal programming, if we just type and just click the play button, it will. So no need to install anything as additional. So you will able to just click the play button. That's it. It will work. Right. So this is a simple introduction about the Google Colab. Now we directly go for the quantum machine learning. Right. So for this quantum machine learning, first we have to install the quiz kit. So that is very important. So in this quiz kit, first you have to install the QuizBit, visualization, and machine learning, right? So I just play this button and just wait for some time. See, once it's successfully run, then you go for the everything is installed. Now we are going to work with the quantum model on a real data set. So for this, we already know the famous one, which is called as iris data set. Three classes, right? Iris setosa, particular, and one more thing. So we are trying to load this iris data set. First, we explore what is available in the data set. Next, we go for a support vector mission. So in general, it is called as a support vector classifier. Then after this support vector classifier, we go for the next one, variation quantum classifier. So this is approach mainly used for quantum computer, right? Then after this, we go for the comparison between the classical and quantum, right? So this is a thing. So first we load the iris data set now. So the iris data set will load up. Now we want to check what is available on the iris data set. So for that, what I'm going to do is I just print that iris data dot descr. So this is nothing but a describe. So describe function which is for handling the data, right? Now we run this in order to describe what is available on the data. Right. So here we will get a complete summary. After getting the complete summary of the data, now, so see here, it is having a three classes, which is iris setosa, versicular, and the next one is and the Virginia. So there are three classes are there, and it is having like this features. And it is having a length, width, and length, width, petal length, and petal width. So these are all the things we have. Now, the next important thing is we have to analyze that data, right? So for that, I'm splitting the futures into that data and the label. So as we already discussed, supervised machine learning is nothing but we have a labeled data, right? So for this, we just put the label, and second thing is we just completed the target, right? this, we are going to normalize the future. Can anyone tell what is meant by normalize the future? What is meant by normalization of futures? Hello. What is normalization of futures? So I mean the values are which we make the values lies 0 to 1, right? So that is a thing. It's a normalization of futures. Now, so for this we are using a component called min-max scalar. So min-max scalar is nothing but it is a process which is for moving, I mean, which is for scaling the data between 0 to 1, right? Then after this, we are using a pandas library in order to visualize that what are all the components available on that data, right? So I just import this pandas. See, after this, so you will get that here there is not that much of correlation, but in the sample width we have some correlation. I mean, some of the points are interlinked together, right? So that is a, and the third one here there is no, and here is also there is minimal compared to the sample width, right? So everything is fine. So once we visualize the futures, then after this, going to train this data, classical, not quantum. So for that, listen, first we have to split the data into training and testing. So for that reason, we go for sklearn.model underscore selection equal to import train split, right? Then second is we are calling the quizkit utils, that is the import the default algorithms, right? So for VQC, variational quantum classifier, we have to call this library. So algorithm globals, right? Then after that, we split that training futures, testing futures, training labels and testing labels. So for that, we fix 80% of data is for training. That is the reason we put here 0.8 and the remaining 0.2 is used for testing, right? So I hope you understand. So 0.8 is nothing but which is for training the data, right? Then after this, so after this thing, I just run that. What happened? It will automatically, the internally what happened? It will split the training data into 80% and remaining 20% to the testing, right? So after this, I splitting the data. So we just call that support vector classifier. So for that, to call explicitly that from sklearn.svm, among that svm, we are calling that SVC, support vector classifier, right? Then After this support vector classifier, just listen. I am just training the futures and training the label. So it will be separated. So see, if you found any error, it will automatically redirect here itself. But if it is everything is working fine, then you will able to get the tick sign, right? Now, once I call that support vector classifier, now internally what happened, the machine learning model will run with this 80% of training data. Now we have to pass the testing data and we going to analyze the performance, right? So for this, listen. So training underscore score underscore C4, this is our name. So svc dot score, support vector classifier dot score, train futures and train labels, right? Then the same thing we are going to find with the test futures and test label, right? So among that, first we classify the performance of training data set, I mean the 80%, and the second is we are going to find the testing, is a 20% of data. That is the unknown data by the model, right? So for that model, it won't have any class label. So it will come, it will substituted to the already trained model, and we check that accuracy. Just wait. Once we run this, what happened? It will give a result for a training data set. It will give 0.99. So as we already know, the accuracy is 100%. Among that 100%, in our classical computer will analyze the data and it correctly classified. 99% of data are correctly classified. And for testing data, the remaining 20% of data is applied, and for that we get accuracy of 0.97. I mean 97%. The classical model will accurate. So as of now, we know our classical computers is very good for processing your data. But what is the major drawback is it can't handle a large number of data beyond that limit. So we have some set of storage capacity. Beyond that limit, we can't able to process, and it takes more time if we increase more data. But in a quantum, we convert that data into a superposition based state, like entanglement, right? So that increases the speed. So as of now, we are completed the classical computer processing, right? So I am just running a simple model. There are a lot of models are there, like a support vector mission. There are a lot of neural network, right? So principal component analysis for selecting the right futures. So everything is possible, right? So this is about the classical computer with classical data. Even though this will be produce 99% of accuracy, this is not sufficient for a complex data, right? So the next thing is we are going to run this classical data on a quantum computer. See, for this we have some basic knowledge about the quantum physics, right? So I will share you the manual. You just go through the manual, you will able to understand what are all the things available in the quantum machine learning, right? So for that, I just call that twisted circuit library. I am importing a Z future map. As I already said, we have a concept called entanglement and superposition and inference, right? So see, this is our input. These four are our inputs. That is the reason it will be represented as Q1, Q0, Q1, Q2, and Q3, right? Then see here, it is having like this plus. I mean, one bit is connected with the another bit, and every bits are connected with each other, right? So this is called as a entanglement, right? So that every nodes are connected with each other, and the computation speed will be very less, right? So for this, what I am using here is I am using a Z future map. So this is the approach for like Z revolution circuit. So it will convert that data into qubits. So in traditional computer, what happened? We directly apply the CSV file and we will run. But in this quantum based computer, can't directly apply the CSV file or a normal Excel file to process. First, we have to convert the data into qubits. So in a normal bits, it is the zeros and one. In a qubit, it is called as a between a superposition between a 0 and 1, right? So Z future map main role is to convert that normal data into qubits. Okay? So once you go through here, you will get all the information about what is how it that normal data into qubit. Okay? Then after that, we are once we call this future map, what we are applying is that num underscore future equal to futures of shape of one. Shape of one means the first, the last is applied as a input. See, listen here. Just a minute, I will just run it and show. Now, what happened? Accordingly, based on the futures, the shape, the values will be passed, and that futures, it's linked to future dimension, and REPS is nothing but initially we work on the default parameters, so that I make it as a 1, and we are asking that to draw the circuit. So depends on the number of futures available, that this will be changed, right? So here we have only 4 values. So that is a sepal length, sepal width, petal length, and petal width. So these 4 parameters we have, right? So that's the reason it will be constructed 4 inputs, right? So this is a thing. After passing all these values, it will be this quantum based circuit is defined, right? According to our inputs, the quantum circuits is defined. Then after this, we just convert this data into the first we convert that, we create a network, we apply a data, and we convert that into qubits. The next thing is, from the library, you are making in the waveform, that is a real amplitude, right? So for this real amplitude, we discuss the based on the number of futures, it will be converted into the qubits. And here also REPS, we are using a 3. So this is a default one. Now this answer. So answer is nothing but this will create a quantum based computer, right? This is a actual flow. Here you see theta from theta naught to theta 15. So there are 15 futures in that data set, right? So all those 15 attributes are linked. So that is the reason it starts from 0 to 15. So now once we run this biscuit library, it will create a network, quantum network like this, right? Everything is based on our data. What is the data we have uploaded? Based on the data, then quantum circuit is designed, right? Then after that, as I already said, so optimizing. So that is a very important parameter. So for that, I am using that Obila is a one of the optimizer in a quantum based. So this will reduce, control the flow of execution. So for this, so I am using a Cobla, right? So once I run this model, so that will be imported. Now I am passing the values one by one to the quantum circuits, right? So for that, I am just using a import sampler, and for that sampler function, I am passing all the values here. Once it is successfully imported, see, now we are going to analyze that graph. In order to identify the objective function, so maximum the objective function we are going to minimize, right? So that is our ultimate aim. So for that, I am using a matplotlib to draw the graph. Listen. So it will we will define all the things, and we will ask these are all my title, and these are all my x label, and these are all my y label. Now the quantum based circuit is ready. The next thing is I am going to apply the classifier. So as I already said, we are in a classical computer we using a svc, support vector classifier, but in this quantum based circuit we have to move for a variational quantum classifier. So it is generally called as VQC. So inside that VQC, we are applying a sampler and the number of futures, and that answer we already created a superposition and entanglement process, right? And then the optimizer. So as I already said, the optimizer we are using a COBLA, COBYLA, and the next is a graph. Graph function is for creating the visualize the number of iterations it will work, right? Then we will calculate the start time and the end time, the total training time. So everything we will able to calculate by this. Just listen. For every data, the iteration will work. Once it successfully run, we will able to identify that what is the number of iteration and where the epoch will start, right? So see, at the starting time, at the 22nd, I mean the zero state, it will be available. I mean the objective function value is 1.7. Again, it will be reduced, and see at the end we will get that value 1.0. As I already said, we have to increase the number of iterations and reduce that. I mean, we have to minimize the objective value, right? So this is a thing we will get, and finally we will achieve the result, right? So see here, the total training time for this iris data set is 147 seconds, right? So after running this, listen, now we are going to analyze the performance of variational quantum classifier. So for that, again the same thing, train futures, train labels, test futures and test label, we are passing it to variational quantum classifier, right? So once we run this, we will achieve on the training data set, we have 0.85, and the testing data set, we have 0.87. So compared to the classical computers, the quantum based ML, we achieve only 85 and 87, right? Even though this produces a poor result, not a poor, it's a acceptable result, but it is less compared to the classical, right? Even though it is less, once we select the significant features, then the quantum result will perform better than the classical learning approach, right? So let us consider now we successfully run the normal classical approaches, and the next one is quantum based machine learning approach, that is called variational quantum classifier. Now the next thing what we are going to do is by using a principal component analysis, we will shift, I mean we will select the significant features which is a main cause for finding the class labels, right? So for that we have a good approach called the principal component analysis, which is a dimensionality reduction method. So among the 100 features, it will pick the 10 features which gives the major importance for that problem. So for that, listen, so we are applying the PCA for the data, right? For our data that is called features. Then after that, we will just plot it and find what gives a more important, right? So among these three classes, the first class, I mean the zero class is called Iris Setosa, I think so. That will be separated, no problem. But these two are somewhat merged, right? So first we have to identify the outliers and remove from this data, right? So for this, listen, once I am applied the dimensionality reduction like a PCA, and then I am going to train with this classical approach, right? Classical approach that we already know, SVC, support vector classifier. Now I run this. See, we have less in normal, I mean without any future selection, we will get a 0.99 percentage. But after selecting the future, we will get a 0.97. And for the test data, we have there in point like 0.97, but here 0.90. But this is a real output of a model. So no need to stick only on accuracy, right? Once we add a more number of data, or once we add a significant data, definitely the model accuracy will be reduced. So don't think that your model achieve 100%. Definitely they won't accept. If you train more and more values to a model, then it will be a good model. Instead of 10 data, if you put a 1 lakh data into that system and train and test, the accuracy will be some higher, but it will not attain 100% of accuracy. So don't think that your model achieve 100%. So it will be around 85 to 95, right? So that is a thing. So now we are running after the future reduction, we will get the output of the trained as well as testing. Now the next is the same way I am going to apply this to my quantum based machine learning, and then for that I will reduce the future, as we already reduced the futures, right? So that futures is applied to the quantum based machine learning model. So for that, in order to create a network and in order to transform it into the qubits, we are using a approach called Z future map, right? So this is an approach for creating the quantum based circuit, right? Once it is applied, then I am applying the Colab optimizer in order to maximize my performance of my model. Now again we call the variational quantum classifier, VQC sampler. So here we are applying a future map and answers and optimizer and the graph. Here is also we will able to find the total time. So this is about after the dimensionality reduction, right? now after a dimensionality reduction, our model will work. See, after everything is over, then we will get that. So here, after, see, before dimensionality reduction, we have 140 seconds. But after the dimensionality reduction, that the same data is run on 33 seconds. So this is the beauty of quantum-based machine learning compared to the normal classical computers, right? So again, the objective, the objective function value and the iteration is also reduced, right? So listen here, we have till 100 it will cross, but after the dimensionality reduction, what happened? So we will achieve before 30, before 40 itself, we will achieve the result, right? So 33 seconds, all our data is trained. Now again we are going to check that accuracy of our model. Listen. Now, the real amplitude of the training data sets is 0.58 and the variational quantum classifier on the test data is 0.63. Right? So now we check with this normal result. So in this, we achieve 85 and 87, but after reducing the futures, we understand that 0.58 and 0.63. So from this, we came to conclude that dimensionality reduction is not an appropriate technique for increasing the accuracy of quantum-based circuit, right? So, but our classical approach will be like similar 99 and 97. There is nothing big difference. But in a quantum-based classifier, what happened? Initially, we have a 85% of accuracy, but after reducing the futures, it will be transformed to 0.58. So it's drastically reduced, right? So this is, from this we came to conclude that this is not an appropriate approach for the quantum based circuits. We will put the data, right? So from this we came to analyze that dimensionality reduction is not always suits for improving the quantum based machine learning model, right? So once we run this, the next thing is we are going to make a future map. This is about a real amplitude. Now the same thing is applied and we will check the number of seconds, right? Just a minute. See, here the same thing applied here also, but the major thing is, so this is on real amplitude and here we are importing that efficient SU2. So this is a library. Again, it will instead of real amplitude, so what we did is we directly apply the as it is our data is available. So that also gives a same result, right? So it is in 39 seconds and for this 33 seconds. So there is nothing big difference between this real data set and amplitude data. So both are performing the same result, right? So now once we check that, see, now the accuracy is gets increased. This is a real actual data, not a dimensionalized data, right? So in this, you will get a 71% of accuracy. It's a acceptable one, right? And for the testing, it is having 0.67. If you add more number of data as a raw, then you will able to, I mean, the performance of the model gets increased, right? Then after this, this is the last step of, we are just comparing the SVC, I mean support vector classifier and variational quantum classifier, and we will analyze the training and the, right? The same way we are using a same amplitude, and for efficient SU2, what is the percentage? See, for SVC support vector classifier, for 4, it is producing a 99% of test score and 97.97 training score. The same thing for variational quantum classifier, it will give 0.87 and the test score is 0.85. The same thing which is applied for a real amplitude for a 2 futures. If it is a real amplitude, it gives 0.58 for the test. And in this variational quantum classifier of 2 futures, which is efficient by using a efficient SU2, we will achieve the 0.71. So from this today's session, we are running a classical data on a classical model, classical data on a quantum computer, and from this classical data, we just change in a real amplitude and efficient SU2 and find that which is the best suit, right? So from this, I conclude today's session. If you have any doubt, you can ask me. Saravanan sir.
Yes, sir.
Yes, sir. From this, I stop today's session.
Okay, sir. So first of all, I thanks to Dr. Sanmugam, sir. Is any of the participants having any queries? So the participants, please don't move. The feedback will be given. Now I call upon Nagitya for giving about the vote of thanks, and we are requesting some international participants for giving the online feedback.
On behalf of my management and our department, I extend a really hearty vote of thanks to our chief guest, Mr. Dr. Shanmugam sir, who spared time from his busiest schedule to grace the world. Today we had an opportunity to hear your lecture, and this will surely be going to use in our future events. Thank you so much, sir.
Thank you.
Now I call upon our student Sneha to give a feedback.
It gives me immense pleasure to extend my gratitude, sir. Your knowledge and teaching method have enriched our understood on machine learning. Thank you so much, sir.
Thank you.
Now I would like to call Sweta to give her feedback.
Your teaching method is the best because students are actively involved in the discussion and discussions are always lively and to the point. I so much believe that all I have learned from you surely be beneficial as I continue to the next phase of my career. Thank you, sir.
Thank you.
People who are participating in online section, do you have any feedback? Please give your feedback. We need your valuable feedback.
So once again, I thanks for the management, students, faculty, the resource people, as well as the today eminent speaker, Dr. Sanmugam, for giving about his valuable suggestions. The feedback links has been shared in the YouTube as well as in the WhatsApp group in the chat box. Thanks for your participation. The e-certificate will come as quick as possible. Thank you for all. Mental issues people. Within a few seconds,